So this is known as the plane angle. Then let me also introduce you to what you know elementary change, or generally, if I say d theta, what I just simply mean is a smaller angle. Okay, a smaller angle theta. That's how you should take it for now. Smaller angle, a smaller change in theta. So in some notations, we start with it. We call them elementary changes or elementary angle. So let's say I've got elementary angle theta, d theta, or a smaller angle, generally smaller, so d theta. Then this is the arc length, this portion of the circumference. So this angle is known as the plane angle. That you already know, plane angle. Okay. What is the formula of this angle? Suppose, okay, this is a circle of radius r. So the relationship between the relationship. So let's say I'm going to call this arc length. I'm going to call it, since it's coming from an elementary angle, I'm also going to have an elementary dl, which is the smaller portion of the circumference. So dl, l for length. Okay, so the relationship, now the question is, what is the relationship between this elementary angle d theta and dl, the circumference, the portion of the circumference, the arc length? So it's dl over r. This is the relationship. Ça c'est la relation entre d theta et dl. Okay, now, so therefore dl, which is the elementary arc length, is equal to r d theta. Very simple. So when you want to know dl, you just multiply the radius multiplied by the angle for you to know the circumference, the arc length in radians. Then this dl is in radians. That is, I won't go deep into radians. It's not in degrees. That is, the interpretation is you're going to have my pi, instead of, let's say, if d theta is equal to 180. So you won't say 180 degrees. In place of saying 180 degrees, you say it's equal to pi. So we don't deal, only in specified cases, all angles are in radians. Instead of saying 180, you say pi. Of course, this elementary theta will vary from 0 to 180. So it can, to 360. Now, what is 360 in radians? 2 pi. So we can say that theta is between 0 and 2 pi. As simple as that. Because it can change, it can make an entire circle. The circle, we said it's 360. Okay. Now, so the relationship is dl over r. I'm only interested in the relationship between the elementary angle and the elementary length. Now, let us now look at the concept of solid angle. So for solid angle, this is something that you guys don't know. So imagine this is a sphere, not a circle. Imagine this is a sphere. Then we've got an elementary surface, that is 80. Okay, maybe this is the surface on the sphere. Let me do something. So imagine this is a sphere. Then we have an elementary surface on the sphere. Okay, this because it's elementary or small, I'm going to call it ds. Okay, then this is the center of this is the center of this what, the center of the sphere. So since this is a sphere, okay, and this is the elementary length ds, and maybe this is the radius. Okay, so solid angle, as you can see, plane angle, the one that you're familiar with, is a 2D angle. Okay, now for solid angle, this is a 3D. If you can see, imagine this sphere is in 3D. As you can see, I'm trying to do my best. So the angle here will also be in 3D. It won't be a plane angle. So this angle is called, this 3D angle is called the solid angle. Now, the most important thing to know is the relationship, just as we said that the relationship between elementary plane angle and the the arc length subtended by the same angle is that arc length over the radius. Okay, here for the we are going to say, so here we're going to have an elementary solid angle somewhere here, okay, which is in 3D. So the omega is going to be equal to the same way ds. We're going to say ds because this solid angle is going to subtend a surface. It's not going to subtend an arc length like the what, like the elementary plane angle. So for the solid angle, it subtends a surface, this surface here on the sphere. Okay, so this surface, so you say what it subtends the surface over, since it's a surface, you say r squared. Okay, then for the plane angle, it's dl, it subtends an arc length, then over r. Then for a surface, it's ds over r squared. Okay, this is is what you just need to retain. You have to know that given a sphere, the solid angle subtended, uh, the solid angle will subtend a surface on the sphere. So the relationship between that surface and the solid angle is solid angle with the notation the omega etegara that surface over r squared, where r is the distance from the center to that surface. Ok? Very simple. Est-ce qu'on a ensemble jusqu'à maintenant? Très simple.
Yes, yes, we are together. But just one more question. Are you recording the meeting?
Yeah, I'm recording the meeting.
All right. Thank you very
Though,
much.
though, though I'm not really okay with telling, I'll explain. So there are two things. We have a plane angle, which we all know here. Maybe I'll say elementary angle. Then I said the theta is just there to depict that this angle is very small. So we call it elementary angle. So the elementary angle will subtend an elementary arc length, which I'm going to call dl as well. D theta for dl. Okay, so there's this arc length associated with d theta. Then what is the relationship between d theta, the elementary angle, plane angle, to the arc length that it subtends? It's that arc length over the radius. Okay, so this is the relationship in radians, of course. Now, solid angle, this is a plane angle, it's in a plane angle. Okay, it's on a plane, not in a plane, it's on a plane. Now,
Excuse me. Your screen is no longer being shared.
on your part, so this is the plane angle. Now, there's what we call solid angle. Imagine this is a sphere, so that angle will subtend, instead of an arc length, it will subtend a surface. By surface, I mean area. There will be maybe an area that will be subtended here by that angle. It's in 3D. This is a sphere. Okay? Imagine this is a cone. And this is the center. What am I writing? Yeah, so we have, this is a sphere. Then this is an elementary surface that has been subtended by the angle. Okay? A portion, a slice of the sphere. So we call this ds, elementary surface subtended by the omega, where the omega is the solid angle. So the relationship between the omega and the s is the s on top over, but this time instead of saying r, like we said in d theta, here we say r squared because this is a 3D angle. Chief Wembe, have I tried to explain to you? Are you somewhere? So therefore, the most important thing to know is the omega is equal to ds over r squared. That's all. Just as the theta is equal to dl over r. Then this is the solid angle. This is an angle in 3D. Are we there, Chimfem? Sorry if I'm not pronouncing your name correct. Now, now I also introduce you to another uh, notion of ds, which is the surface area. Ds as a vector. Okay, there we're just dealing with ds as a magnitude. Now let us look at ds as a vector. So if you've got a surface, an elementary surface that you're calling ds, okay, then you have a vector normal to it. That is the angle between the surface and this vector is this vector is perpendicular to the surface. We say the vector n is perpendicular to the surface, to the surface ds. So we say the vector is normal to the surface. So the notation ds, this is used to represent the surface, the magnitude, that is the surface, and the normal vector to it. This normal vector has to be a unit vector so that the magnitude of ds will be ds just. So whenever you see ds, that surface as a vector, so far we're talking about ds as a magnitude. Ds as a vector is just the magnitude ds and a unit vector that is normal to that surface. So I don't know if I'm communicating. I don't know if you understand. Because you should, we're no longer going, we're not just going to be dealing with ds alone. We're going to be dealing with ds as a vector. We can vectorize, that word exists. We can vectorize a surface. So whenever you have a surface can be, maybe imagine this surface. Then we're also going to imagine a vector normal to it that is coming out of the screen. Provided that vector is perpendicular, imagine this vector is coming out of the screen or pointing towards you guys. So if this vector is a normal vector that is normal to this surface, so ds, if this surface is called ds, when I say ds, I'm just talking about, well, I'm studying a smaller portion of the surface, will be written as the magnitude, which is ds, then with a vector normal to it. As simple as that. Now, so let's go back to solid angle. So if I've got a sphere, then imagine solid angle is not a plane angle, it's an angle in 3D. Just to put it in simpler terms. Then I slice off a portion of this sphere. You know what a sphere is? Okay, I'm not an artist, so but don't imagine this to be the circle. Imagine it as a sphere. Then I slice it off. Okay, then this is the elementary surface that I've sliced off. In short, you have a cone. This is a cone. Okay, then we said d omega will be equal to ds now as a vector. Okay, ds as a vector over r squared. Okay, this is what you need to retain. Okay, so we said that the omega will be equal to ds when we're not talking about magnitudes over r squared, right? But when we're talking about vectors, it will be ds dot ur. okay, in terms of vectors, and we're not going to be dealing with this formula. We're no longer going to be dealing with this formula. I just wanted to show you step by step method. So you should get used to this type of mathematics, which uses vectors. So ds dot ur. When I say ds dot ur, I mean, you see this is the vector, the unit vector ur. That is this this is the distance, this is the radius. Now there will be a unit vector associated to it. Last time I talked about what unit vectors are and um, how we use them. So we had the radius r, so a unit vector in the direction of. So let's say if I want to represent this vector or I'm just going to say the magnitude multiplied by the unit vector, just like that. So you get ds, then you dot it to ur, and then you guys have you started learning mechanic du poids, scalar product. So a scalar product will give us a scalar product of two vectors will give us a scale. This is why this angle, the omega, doesn't have an r on top, because this product here, this dot product, will give us a scale. Okay, so everything will be a scale. So vector wise, the omega. So I'm now going to give you the formula that you're going to be using on solid angle. So this is how you do it, and this is what I expect in the homework. Okay, so follow with me nicely. So this is how you construct. The question will be construct a well-labeled diagram and to derive, we're going to derive the formula for solid angle. Okay, so the first thing that you're going to do is you're going to start with a cone. That cone that you sliced off, okay, we start with a cone like this. Okay, then this side is the surface ds. Okay, now we're going to draw a vector that will be normal to the surface. Imagine this is coming all the way in the middle, then going out. So this is the normal. So this vector is such that it's perpendicular to the surface. So imagine this is your surface. Okay, then ds. Therefore, ds as a vector will be ds multiplied by the unit vector that is perpendicular to this unit vector that is perpendicular to the surface. Then this unit vector is also connected to this line, which is all the way from the point O in the middle. Okay, this is the first thing that you do. Second step, you parameterize your cone. We all know cone ice cream, so you can start from there. So this then I'm going to call it L. Normally it was radius, but since this is a circle, will have radius. Therefore, you say this you use another data. You say L. So even this one is L. Then this side which is inside, you call this distance A from here to here. You call it A. Then all the way there, this is radius. So you have this rectangle. Then you call this angle alpha. This is how you parameterize your cone. Okay. So you have from your cone you have this uh, triangle with parameters L, this side A, and this side R, because from this point to this point, this is the radius. So this is how you parameterize it. Oh, we know that elementary solid angle is given by ds, the surface that it subtends, you dot it to ur. So in this case, it's not going to be ur, it's going to be ul. Now the question is, what is ul? Ul is just the unit vector. Did it teach unit vectors? A unit vector in the direction of UL. I tried to teach you unit vectors. So you've got the length L. Now UL will just be the unit vector. When I say unit vector, it has got a magnitude of 1. Okay. So you dot ds, you dot it to UL. then over L squared. That is this length L squared. That's the only thing that you need to know. Then from here, you start breaking it down. Mr. Honest, when I've got 5 minutes remaining, let me know.
Sure thing.
Not We're going to call this R because it's a radius, of course. Then you're going to call this angle alpha. Okay? Yeah. Then by definition, solid angle together ds as a vector, you dot it to. Then you're also going to define a unit vector. This length L, you're going to attach a unit vector to it, and we're going to call it unit vector L. So you say unit vector L. It's a unit vector. Then over L squared. As simple as that. Now, here we're going to try to express the omega as a function of alpha only, which means the right hand side of our equation, only has to have alpha in it. That is, ds has to be broken down in such a way that we have alpha. So when you reach this point, very simple. Now you've already parameterized your cone. Therefore, it will be very easy to do it. So we're going to use um, math to do it. So we're going to start with ds. Okay, we know that ds by definition is equal to the magnitude ds, then the unit vector, the normal vector, the vector normal to it, and this is a vector normal to it. Okay, now what is ds? ds, okay, so s is the surface area. Now the surface area, this is the area of a circle, and we all know the formula of area of a circle, which is pi r squared. Okay, this circle will have a area of pi r squared. Now here your main area of interest is ds and not s. Therefore, you're going to say ds. You're going to derivate. ds also it signifies elementary change. At the same time, d signifies differentiation. So ds over your variable here is the radius. Okay, so ds over dr is equal to, that is, find the derivative of this with respect to r, which is going to give us 2 pi r using the power of, for people who have forgotten differentiation. So now here I want to extract ds. So ds will be 2 pi r multiplied by dr. As simple as that. Therefore, you've dealt with ds. But in ds, you also have the radius. Okay? So when then you also have dr. So you have to get rid of r and dr. Don't forget, we want to express everything as a function of omega alpha, because alpha is the angle. So we want to get rid of anything that is not an angle on the right hand side of our equation. So we've broken down ds as a function of r, but we also have to break down r and dr finally as a function of alpha, because our main goal is to make sure we don't have alpha on the right hand side. Yeah, so now how for you to find the expression of radius, you use this rectangle. You have got radius here. So you're going to use tan. You can use sine, cos. You try which one will give you the radius as a function of alpha. But for me, I'm going to you use tan. Tan is the ideal one. So tan alpha is equal to, we know tan of the angle is equal to the opposite, which is the radius, over the adjacent, which is a for now. We parameterize this length to be a for now. Okay. Then what you need is your radius, because here you need to get rid of radius. So radius will be equal to a tan alpha. Therefore, you managed to express radius as a function of alpha. Now, the next thing is dr. How are you going to deal with dr? The same, in a similar way that you did with You've got r, so you just say dr over d alpha. Whenever you do this, you're differentiating the radius with respect to alpha because alpha is the variable here. The same way you did here when you had s, you know that s is equal to pi r squared. So you say ds over dr for you to get t. You differentiate with respect to the variable. Now here what we want is dr. This is why we had dr over d alpha. You know what this is differentiation. Now an interesting thing is a is a constant. Okay, so here you just need to know how to differentiate t tan alpha. Don't worry, you're going to get used to this. Now, for you to differentiate tan alpha, I'm going to remind you, or for the people that didn't know, I'm going to give you an expression. Tan alpha can also be written as cos a sine alpha over cos alpha. Okay? Then, how do you differentiate? You can now apply the quotient rule because you've got a quotient sine alpha over cos alpha. What does the quotient rule say? Very simple. Okay? We're trying for me and the Moroccans, your fellow students and Moroccans, they already know the derivative of tan. They know that the derivative of tan alpha with respect to alpha is just 1 over cos squared alpha. But for you guys, I'm going to show how many minutes. Just say okay, just what it's 1 over cos squared alpha, the derivative of tan alpha always. But I'm going to show you why it's like this. Okay. One good thing about Moroccan education system is that they have been taught to, I don't know if it's to memorize. They are very good when it comes to differentiating sine, cos, what, trig identities. They are very good. They don't even like waste time. You don't have to do this, but in my homework I want you to do this as well, just to show me where you are getting that 1 over cos squared alpha. Okay, so if you follow step by step, don't give up. Don't give up. Okay, this is the type of mathematics that you need to get used to, as I told you in the introduction. So this topic also introduce you to a certain type of mathematics and reasoning. So now, how do you do with the quotient rule? For the people that have been learning with me and the people that have been following me, I've taught you the product rule and the quotient rule without having to remember the formula. So this is how you do it. So for you to find the derivative of sine alpha over cos alpha, you just simply say, you first find the derivative of what's on top. Also, for people that have been learning with me, I've taught them that the easiest way to remember, if you want to know how to differentiate sine and cos, you make this thing that I've made here, and then, for example, here I'm going to say the derivative of sine. So for me to find the derivative of sine, I have to go down. So whatever I find first is the answer. So meaning sine, the derivative of sine is cos. So the derivative of cos will be negative sine because I'm going down. In integration, I'll go the other way. Okay, as simple as that. So the quotient rule says you integrate what's on top. So you differentiate what's on top, sorry. So what's the derivative of sine alpha? So the derivative of sine alpha is cos alpha, you go down. So you say cos alpha, then you multiply by what's down. So multiply by what's down is cos alpha. Then you subtract, you now do the opposite. You find the derivative of what's down. So what's the derivative of cos? The derivative of cos will give us negative sine from this card diagram. It's very helpful as you've seen here. So the derivative of cos will be negative sine. So negative sine here, sine alpha, sine alpha. Then you multiply by what's on top, okay, which is sine alpha. So at first you differentiated what's on top, then you multiply by what's down. Now you say minus, this is how you do the quotient. So for any quotient, you now find the derivative of what's down, then you multiply by what's on top. Very simple. Then over what's down squared. So cos squared alpha. So let me try to simplify this. I'm going to have cos squared alpha, then negative negative will give me plus sine squared alpha over cos squared alpha. Now, From people I did additional mathematics, if you didn't do additional mathematics, no problem. This is why you are doing these ones. So we know that cos squared alpha plus sin squared alpha is a very famous identity which is equal to 1. So for people that didn't know, take note of this identity. So whenever you have cos squared alpha plus sin squared alpha, this is equal to 1. So this is going to give us 1 over cos squared alpha. Therefore, ladies and gentlemen, we have found the derivative of tan alpha. So for the Moroccans, they are very brilliant when it comes to memorizing actually. So they know derivative of tan alpha, sec what. But if you've forgotten, you can just do this. Okay, and from my homework, I want you to show me how you found 1 over cos squared alpha. Okay, but for me, even me hapa naomba wadinsa mko Moroccan. Whenever I'm differentiating tan alpha, we'll just go direct ma. So here, we'll come back here. So the derivative of tan alpha is 1 over cos squared alpha as shown by this. You also have to remember that tan alpha is equal to sin alpha cos alpha. I'm going to remind you about these identities. For people that didn't do additional mathematics, don't worry. INFM identities you'll be using almost the same identities, just know them. Next time when they talk about them, you like remember, oh okay. And that's how you know. You don't even have to like start learning identities and things like that. No. Whenever you find a certain identity, you take it as the way it is. That's how you learn. You don't have to panic and things like that. How many minutes am I remaining with? 4 minutes. Okay. So guys, don't forget, we're coming back here. So therefore, our dr is equal to a over cos squared alpha, then you multiply by dr, because what we want is dr. So don't forget, our objective was to get rid of radius and dr. So for you to get, first of all, for you to get to, okay, with the 4 minutes, I'm going to summarize. So you first write, once you parameterize your cone ice cream, right? Once you parameterize your cone, you write the formula. The formula of solid angle is equals to ds dot ul. You have to know where ul is a unit vector and l, then ds is the surface with a normal. Okay, the surface with a normal. Okay, dot ul over this length squared. Then the second thing, now you start getting rid of ds. So here you write ds is written as ds and the norm. So what is s? Okay, s is the radius, the surface, the area, surface area of this circle by r squared. We all know the surface area of a circle by r squared. Then the variable here is the radius, so you differentiate ds over dr, because what you want here is ds, elementary change. So ds over dr will give you 2 pi r. Okay, so which means ds will give you 2 pi r dot dr. Oh, you also don't need the radius and the dr. Therefore, from here now, you're using tan. This is why you have to make this rectangle. So you know that tan alpha is equal to radius over a, this distance adjacent. So therefore, radius is equal to alpha tan a tan alpha. And then the variable here is the radius, this angle alpha. So you're going to you also want the expression of dr here.
Yes, Peter.
Okay, so I understand some things will be strange to you. Mr. Honest, est-ce que tu peux voir mon écran?
Oui, 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 c'est clair.
Oh, d'accord. Shukran bizarre. So the type of if you get used to this type of mathematics, this is why I like the concept of solid angle. It will just try to follow through and you learn a lot of things. Yeah. So your engineers, don't give up. So I found an expression of the r and r. So our main goal was to make sure the right hand side doesn't have anything else other than the angle alpha. And of course, when you're talking about as a function of alpha, alpha is not never alone. Always moves with sine, cosine, sine, cos, and tan. So whenever you say a tan alpha, you see how a will disappear. You will see. So I've now found an expression of 2 pi r and dr. Found an expression of r and dr. Now, here, what is needed to do is finding an expression of L, and so L squared. Now, L is the hypotenuse of this triangle. Very simple. So we're going to use cos. You can try sine, cos, tan as well, but the one that works is cos. Best. The one that works best is cos. Okay? I'm sure we all know Sokatoa where I'm getting this. Okay? Cos alpha together. So cos is equal to adjacent L. Oh, no. Adjacent A over the hypotenuse. Why we're using cos? Because we can't choose sine, because sine will give us the radius. So A over L. So therefore, don't do um, L is equal to A cos alpha. In this way, we've managed to express L as a function of alpha. Don't worry about A, it will disappear. So I think I've done everything. Once you do this, the S, you'll have to identify what your S. Oh, the S is the surface area. This is the area of a circle. So now I'm going to go back. So you also have to memorize at all costs the formula for solid angle. The omega together ds dot ul. You also have to know what ul is over. I don't know how the guy is teaching you and what he's teaching you. I hope things have to do with unit vectors. What there should be something that should be clear by now. Is that someone who wants to join? Is there's a hand? If there's a hand, people. Yes.
No, I wanted to ask for the way you wrote the last equation. For A, isn't it supposed to be like A over cos?
Yeah. Thank you very much for that observation. Yeah, it means people are following. Yeah, I made a mistake. Yeah, I made a mistake here when I express L as a function as a what? Then with the homework, see, we try to understand and try to replicate everything on your own. Don't try to code them. I will know. I will know. The funny thing is, I will know if you phone them, but if you uh Fiakusanan. And then in life show yeah, so here L should be A over cos squared alpha. Thank you very much, Mr. Basil, for that remark. Okay, so we continue. Um, what is it? Yeah. So from the formula, we said that ds, this is the magnitude, by the way. It's not a vector. ds is 2 pi r dot dr. This is the magnitude, it's not a vector. The vector, ds is the magnitude, then multiply it by the unit vector, the normal vector, the normal unit vector. This vector is such that it's perpendicular to the surface. Okay? And then, so, now, if the guy taught the dot product, if I told the guy taught the dot product, uh, I'm also going to remind you, the dot product by definition is defined by, you get the magnitude of ds, then you multiply it with the magnitude of the second vector, which is ul, then you multiply it with the cos of the angle between ds and ul. So now the question is, what is the angle between ds and ul? So let's go back. So ds is the same as ds with a normal vector in the direction of the normal vector. Okay, so let's go back to our diagram. We always make reference to our corner script. So you have seen this normal vector. This normal vector is in the same direction as this entire thing, right? And this is the unit vector in the direction of L. So this is where the direction of UL. This is the direction of N. So what does this imply? This implies that the angle between N and UL is alpha. Okay, the angle between N and UL is alpha. So the definition of dot product, if you don't know, then you have to know now. Whenever I've got two vectors, you get the magnitude of the first vector, you multiply it with the magnitude of the second vector, then you multiply it with cos, the cos of the angle. For people who did the additional math, and if you can remember this formula, cos of the angle between them. Now, you identify what is the angle between ds. ds is none other than the direction of ds is the normal vector here. Okay, so this is why we looked at the normal vector. Okay, very simple. Now, what is the magnitude of ds? ds can be written as ds is written as ds is written as the magnitude with a unit vector. So the magnitude of ds is just ds. So here I'm going to have ds because the magnitude of a unit vector is 1. 1 times ds is ds. Then multiplied by, this is a unit vector by definition, ul. So then its magnitude is 1. Then cos of, okay. Now, the question is, this is how we do the dot product. Okay. So, from your formula, you're going to go out the dot product. So the magnitude ds multiplied by the magnitude of ul, which is just 1, then multiplied by the cos of the angle between them, which is alpha, over l squared, sorry, l squared. That's it, according to the formula. So now, I've already found what my ds is. My ds is 2 pi r dot dr over l squared. Okay. I've also found what my R was. Using tan and the cos, I found R dl. So the expression of R was A tan alpha. Then the expression of dr, we just identify you have R, then this is the variable alpha. So you just say dr over the alpha. That is, here you can also apply the product rule because you've got a product of two things, A and tan alpha. But A is constant. For people who attend my other lessons, I've overemphasized actually on the product rule. Whenever you have the product of two things, A and tan alpha, you apply the product rule. Then the product rule, just as we applied the question rule, we just say you first differentiate the first thing. So the first thing, which is A, what's the derivative of A with respect to alpha? A is not changing as alpha changes. Therefore, A is 0. Then you multiply by the second thing. Then you say plus the derivative of, you now keep, you now maintain the first thing. Then you say, what's the derivative of the second thing? What's the derivative of tan alpha? 1 over cos squared alpha. I've shown you why it's like this. For now, so which is, if I multiply, I'm going to have this expression. Therefore, this is why when we had dr over d alpha is equal to A over cos squared alpha. Now, in our expression, we only have dr. We don't have dr over the alpha. So therefore, we are going to express dr as a function of the alpha and alpha. So it's going to be A over cos squared alpha, then the alpha. You multiply the alpha this side. Yeah. Then you also have got your R. Then your L, we also found it. The one that is just from correcting me, it's A over cos alpha. So here we have got L squared. So I'm going to square this side. So L squared will be A squared over cos squared alpha. Whatever is remaining now is just the 1 plus 1. I'm just going to replace it. So I'm going to have 2 pi r. No, where there's r, I'm trying to get rid of. R was A, but for simplification's sake, I'm going to say it's A tan alpha, but I'm going to put A sine alpha over cos alpha. For now, you see why it's not important to know. I need to know trig, I need to know a bit of additional math. You see why it's important? It's important because from the other things that you've learned that tan alpha for the people that didn't know, is equals to sine alpha over cos alpha. So hapa ungaifake hapo chape. Hii identity you've learned it today. Okay, you will learn out of identities through the exercises. Then a sine alpha over cos alpha. Then yeah, that was that. Then dr was multiplied by a over cos squared alpha. Yeah, then d alpha. Don't forget about the d alpha, the expression of dr, which are just from finding. Then everything on top. Then what is L squared? L squared, we found it to be a squared over cos squared alpha. Then here you do none other than you just start simplifying things. You see here we had an expression of tan alpha. So we had to change it to sine and cos because we can cancel. You know what? We can cancel out. Yeah, no, I think I've forgotten something. So here it's going to be ds cos alpha. I forgot the cos alpha part because this is ds. So ds multiplied by cos alpha here. So here we're going to have cos alpha here. Okay, I just forgot this term. So you just cancel out now. You cancel out this term. You cancel out this term. This and this, mathematically, this and this will cancel. If you want, you can just try to cancel. You all know the matter of cancelling out, dividing. Then this and this will cancel. So beautifully, my d omega expression will now be as a function of 2 pi. 2 pi, by the way, I said I talked about radians. 2 pi is 360. So this is a constant. 2 pi, then I'll have sine alpha, then d alpha. As simple as that. You've expressed your 2 pi as a function of alpha. The alpha is an elementary change in alpha, so it's also a function of alpha. So, ladies and gentlemen, we found an expression for elementary solid angle. So, in some books, they'll just give you this one directement. Then, of course, there are other ways of demonstrating, but this is the best way for you to even learn some other math. So there are other ways of demonstrating this. So if you can memorize, because if you can memorize this expression, all this work that we've done here is unnecessary. It's just for practice sake and learning different things. If you can memorize this expression, you're good in an exam. Maybe I'll just ask you, donnez-moi, give me, I'll call this solid angle, elementary solid angle formula. So you give me this formula. Okay, so I don't know if you've got questions. I'm sure I know it's a lot, but if you watch this video, you go through step by step the same steps that I've gone through. If you do it, this will carry a lot of marks. We're not going to take it anywhere. You've seen like I'm pausing some parts of the video to explain things that are necessary. So sometimes I forget. So when you're watching this video, you find some cuts. This is why I don't advise like for people to just watch videos. Okay, but for you guys who are following, you understand. Okay, now the next question is now for us to find omega. Okay, so whenever you have, we represent a smaller omega by d omega, that is the differentiation of omega. So if you want to find omega, since this is derivative or differentiation, for us to find omega, we do what? We integrate. Okay, for us to find a smaller thing, we say differentiate. For us to find the entire thing, we just integrate the differentiation of the omega. So what I'm trying to say is, once you find this expression, you're also going to learn something. So to find omega now, that's the next question. You're just going to integrate the omega. So we're going to proceed and put an expression of the omega, which is 2 pi sine alpha d alpha. Okay, now I'm going to remind you as well, with the rules of integration, if you've got a constant, you can take it outside. 2 pi, then the integral of sine alpha d alpha. Now this integral has to have bounds. So alpha is an angle that varies from 0. Now, this second question hasn't specified the exact, because this omega, we've expressed the omega, or omega will be a function of alpha. So it will depend on alpha. To remind you what alpha is, this is alpha. Okay, so this angle varies from 0 to 180. Okay, so the angle alpha varies from 0 to 180 to pi. 180 is pi. Okay, so from 0 to pi, or p, as they say it in French. So from 0 to p. Okay, so now the next question hasn't specified like the value of alpha. So you're just going to assume. The next question has just given us to find the whole thing because we just found the smaller thing. So for us to find the whole thing, but we don't know. Yeah, but we don't know. We don't know. Here we're integrating with the respect to alpha itself. So we don't know. So alpha will vary from 0 to what? You just call it theta because you don't know the exact angle of alpha. But you know that alpha varies from 0 to pi. Okay? In total. So you're going to say, okay, we're going to suppose that our alpha is theta. So we say from 0 to theta. And here we're not going to say alpha itself because here, whenever, for example, if you're integrating x with respect to dx, you can't say, if you don't know, you can't say from 0 to x. No, this is not allowed this is not allowed in mathematics. In the mathematics, you're going to use another variable. You're going to say t. Since here we've got x dx, so since here we've got alpha d alpha, here I can say, okay, my alpha varies from 0 to alpha. So here I'm just going to use a different angle to obey the rules of mathematics and just for it to look clean and neat. Okay, so here now I'm going to introduce you to the same thing. They are going to assume that you know how to integrate. So for me, I'm going to teach you this kind of thing. It's just what I use. So I said that whenever you're differentiating, you go down. Okay. Now, whenever integrating, you just do the opposite because you know that differentiation is the opposite of integration. So here we're trying to integrate sine alpha. So what is sine alpha? The derivative of sine alpha. So I've got sine. So for me to integrate, I mean, what's the integration of sine alpha? So for me to differentiate, I have to go this way. Now for me to integrate, I have to go this way, the other way. And this is clockwise, then this is anti-clockwise, anti-differentiation, anti-clockwise, if you want to remember. So the derivative of the integration of sine alpha is, so you put it in here, you say that the integration of sine alpha is negative cos alpha, from where alpha is moving from, it changes from 0 to theta because you don't know. The second question hasn't specified. Okay, so whenever you are moving from the omega to omega, just integrate the omega, very simple. And then you're going to say 2 pi. Then here you're going to put you're now integrating. You know how to integrate. So uzambira upon a theta, then minus cos. Then here, oh, you start with theta. Then here you put 0. Yeah. Now, yeah, it's like this. So negative, negative. So it will be plus because here when you subtract, you know how to integrate. You put the bounds. Okay, so 2 pi. So cos 0, you should know cos 0. You can put it on a calculator, and whenever you are using a calculator, put it in radians. For those that don't know, you can check somewhere how to put your calculator in radians. So cos 0 will be 1. 1 minus, this theta is not specified. So you just leave it the way it is, cos theta, because you don't know the exact theta. So the solid angle on which you see a disk is generally given by 2 pi 1 minus cos theta. As simple as that. Then the elementary solid angle is given by 2 pi sine alpha d alpha. Okay, so it just depends on what they have asked you. Find the solid angle. This is what you find. Find the elementary solid angle. This is what you find. And from here, we just integrate for us to go there. Okay. Now, the third question is donner l'angle solide sur lequel on voit les demi-espaces. Okay. So, l'angle solide dans lequel on voit les demi-espaces. When they ask this question, demi-espace, okay, this is now where you now get into the specifics, because here we said we didn't know the value of theta, the exact value of theta. Okay, so for you to see half of the disk, for you to see the demi-espace, half of the disk, you we said that theta alpha varies from your diagram. Alpha varies from, I know it's a lot. Alpha varies from 0 to pi. So for you to see half half of the space or half of this disk, demi-espace means half. So you have to, your alpha has to vary from 0 to pi. So that theta has to be, oh, pi over 2. So from here to pi over 2. If this is pi, pi over 2 is 90. As I told you, get used to pi instead of 90 degrees. Ile mwareveresha kuna kuvaiti. So, so for the second question, you just say theta is equal to pi over 2 for you to see half of your surface. For you to see half of your surface. So you now they have now specified. So you've seen. So the second question didn't specify. They just said give us a solid angle on which we see the surface. Now they haven't specified which surface. So you just suppose that angle is theta. Now here now they have now specified that theta is pi over 2. Half we just say pi over 2. Then the entire surface you say pi. Okay, because here alpha varies from theta to pi. Okay, so demi-espace, pour voir the demi-espace, for us to see the demi-espace, I'm sure you've been seeing this way for you to see. So solid angle, when you're looking at the surface on this side, this is the solid angle at which you're going to see this surface. So if you want to see half of the surface, you just say theta is equals to pi over 2. So the work was in finding the elementary solid angle. Then you can now find this solid angle by integrating. Once you find this solid angle, you just, because you don't know the exact, if you are seeing the whole surface, the mid surface, or a certain portion of the surface, you just say theta. Then you integrate. Then once you integrate, the other questions you just be pausing. So for example, this question is saying demi-espace, you just pause. Okay? We're from finding elementary, not pi. So a solid angle is equals to 2 pi 1 minus cos theta. In some books, you just find they've given you this formula directement. Yeah, they haven't like derived it and things like that. Then, so pour voir demi-espace, on pose theta est égal à pi sur d. Okay, therefore going to have dp 1 moins cos p sur d. Moroccans are very sharp. P sur d, they already know what it is. So 2 pi 1 minus, so what is, c'est quoi, you can just put cos pi over 2 in the bracket. It's going to give you negative 1 if I'm not mistaken. No, it's going to give you 1. Wait, I have to have 1 here. C'est quoi P sur D? What is P sur D? Where is my calculator? Calculator hapa. Okay, I have it. Cos P sur D. My calculator is right there. Degrees. just a minute. The solid angle on which I'll see uh, half of the surface, this was the surface of the cone, is 2 pi. So from now onwards, I can just ask you a question. What is the solid angle on which I can see half of the surface? You just say 2 pi. You find it or you say 2 pi. But you also have to know it is 2 pi even without finding. But I'm not interested in 2 pi now. We're now going to find the solid angle in which we can see the entire surface. And this solid angle, we're going to use it later when we start looking at things like magnetic flux, okay, or electric flux. We talked about electric field the other time. You understand better. We're going to use the concept of solid angle. So now, our expression of omega was 2 pi 1 minus cos theta. So the next question is, what is the solid angle on which we see the entire surface? Very simple. This time you say theta is equals to pi. So solid angle is equals to 2 pi 1 minus cos pi. So what is cos pi? 2 pi. What is 1 minus cos pi? Cos pi. Cos pi is going to be negative 1, yeah. Yeah, so cos pi is going to be negative 1. So this is going to be 2 pi multiplied by 2, which is going to be 4 pi. So I'm going to say the 4 pi going forward. Please remember this. So the solid angle, so here, not me mixing French and English, the solid angle on which, also like it, on which we see the entire surface is equal to 4 pi. Then half of the surface 2 pi. We're not going to be using 2 pi a lot, but 4 pi. Then the other things that you just need to know is finding the elementary solid angle, which has got a lot of work to do. This will be equivalent to 14 power of your homework. So the expression was this. Then you just integrate. When you integrate, you find that you're going to have 2 pi 1 minus cos theta. It's going to be as a function of theta. Then you can now go to specifics. Demi-espace, you say poso theta is equals to PSU day. Then I don't know if it's tout espace, poso theta est égal à P. As simple as